All right, so this is the lecture that I really want to go over many details about machine learning and deep learning, like neural network part. In the past couple lecture, we have talked about like basically forward propagation, backward propagations. So basically, forward propagations, we can calculate the loss. Backward propagation, we calculate the gradient. Then we use the stochastic gradient descent or mini batch gradient descent to update the parameter using this gradient information. So this is very, very straightforward way, and you have seen this kind of like style um, in other machine learning models in the past. But the difference is in deep neural network or neural network models, the backward propagation to calculate gradient is the key. So actually, the most difficult part is actually the step 3. So Um, let me put the view full screen. All right. So I hope this is good. Let me see. Okay, good. So today I'm going to talk about training neural networks, right? So this is a very important thing, and you are going to experience that in your homework, how to efficiently train the neural networks. There are a lot of things that, like evolved, for example, in one-time setup, you have to choose your activation function, how to pre-processing the data, how to initialize the weight, how to regularize that, how to do the gradient check. So all these like things that you have to set up before you actually train your models. Then there will be a training dynamics. That means you have to babysitting the whole learning process. You have to monitor the parameter update. You have to do hyperparameter optimization. There are a lot of things that you can do. Because in neural network, the parameter is so many that have to and that you actually have to be very, very careful here. At the end, you want to do um, like model ensembles, test the time and augmentation and transfer learning. So some of this I don't have time to talk about in this semester. Many of material will be postponed into 593. Okay, so for this, this is Jake's question in the last lecture, how to choose those activation functions, how to do these kind of weight initialization. And I will talk a little bit on the batch normalization. So today, I'm only going to cover the part 1, which is one-time setup. In the next lecture, once you come back from uh, Thanksgiving, I'm going to talk about the training dynamics. So I will cover a little bit on evaluation, but transfer learning, something like that, will be postponed into 593. All right, so activation functions. So we have a talk about 3 activation functions already. One is sigmoid, one is hyperbolic tangent, one is ReLU. So you can see the one on the left is the one that we already talked about. There are more, like say leaky ReLU. So let me just, I don't need this. I don't need this. Okay, okay. I, okay, so there will be leaky ReLU, which is kind of like it's like the one that you see. This is still like discontinuous, but once it's less than 0, and the like function looks like 0.1 times x instead of x. Max out ELU is also a very famous one. So basically, this whole thing will be smooth transitioning. It looks like ReLU, but it has negative values when x is less than 0. All right, so we are going to talk about this one by one. So first thing, like this is the activation function of the sigmoid. We have seen this sigmoid before. So basically, it squashed all the number to the range of 0 to 1. Was used to be very popular because the reason being popular is this actually can mimic how the neuron fires. So they can actually has a very good interpolations as the like firing rate of neurons. So and what does that actually means is you can think about neurons once they passing the z equal to 0, they will start to fire. So that's why like I mean this is being like and approximated by the sigmoid. But okay, so what actually see in a neuron, it will be like step function. But of course, it's like step function is really bad. So we are using the sigmoid to approximate the step functions. All right, so next. But there are three problems. We have a talk about this first problem in my lectures, which is this like saturated neuron will kill the gradient. For example, this is the one that we have seen it before, so right? So this is sigmoid and activation function. I mean, this is the input. So like what we have is we have gradient of the sigmoid output, then sigmoid output and the gradient with respect to x. But the gradient sigmoid with respect to x give you something like that, sigma, and a sigmoid times 1 minus sigmoid, right? So this is the something that we have seen before. But if we are at value of minus 10, we actually get and the sigma will close to 0, then the derivative and partial sigma partial x it will also be 0. So that means if we are in this very negative values of my x, it actually will give me like nearly 0 derivatives. So, yes, yes. So that's why the partial L partial x will actually give you close to 0. Then you have a problem. So you don't have any like direction that you should go in the stochastic gradient descent.
So when we're looking for activation functions, it's nice to know that we're looking for functions where the derivative is rarely 0. Is that correct?
It's not exactly the cases. It's um I mean you will see later on, but
Okay.
I mean so yeah you can still have a like zeros, but the things you want to see in practically speaking, you don't want this kind of gradient vanishing to happen. So this is the phenomena of the gradient vanishing. So gradient vanishing is exactly the cases that although you are not in optimal value, but your gradient is already close to 0. Okay, same thing if it is 0, then actually it can do very good job because partial sigma partial x actually will be the maximized at a point of 0, which is equal to 1. Say like similar issue will happen when x equal to 10. Likewise, I'm x equal to minus 10, the gradient will also close to 0. Okay, so I mean, this is an like similar issues with the minus 10 or 10. So the thing of x, the input before and before the sigmoid, if the value is very extreme, super positive, super negative, then we have a problem. If the value is being concentrated around the 0, then we don't have a problem. Right, so this is the plot of the derivatives. Okay. So as I said, if like all the gradient falling back to 0, then the weight will never change. So we have a problem. Okay, so that's the first problem. The second problem is sigmoid output are not 0 center because the output of sigmoid is between 0 to 1. I mean, instead of minus 1 to 1, right? So this is something that you have to be worried about. So think about your input to a neuron is always positive. That means your x is always positive, right? So what can we say about the gradient on w, which is my weight, right? So this is the x0. I mean, so w0, x1, w1, x2, w2. These are the linear combinations of w and x. So this is give you the linear transformation. So think about your x is actually all positive. So your gradient sigma we're using sigmoid, which is sigma times 1 minus sigma, partial L, partial X is the simple chain rule right here, right? Okay, so if we actually plug in this right here, so here, my F is my sigma and a sigmoid. Then this is we like literally plugging the input from upstream, and this is the input from upstream, right? So this is and the contribution from partial sigma, partial X, and this is the contribution of partial L, partial sigma, which is the X right here, and also there will be some upper like stream gradient, and through the chain rules, right? So this is the derivative that you will find for the partial alpha, like partial W. Okay, so the first thing is this part is always positive, right? Because you can literally plot out, it looks like Gaussians, but you know the value will never be negative here, right? And also we assume X is always positive, right? Because we know this is the output from the previous layer, from the previous sigmoid. So the X is also and a positive. The value in the pink box and the value in the red box, they are all positive. And this upstream gradient, it's also a scalar. So the sign of the gradient for all the Wi will have the same sign of the upstream scalar gradient, right? So that means the sign is solely determined by this upstream gradient, no matter how and what value it is. So this is really a bad sign because your current W, the current weight at the current layer may not be the optimal. Some weight, need to increase, some weight need to be decreased, right? But here, what you say is they can only decrease by the same sign as the upstream scalar gradient, which is really, really bad. So this is what will happen if my input of neuron is always positive, right? So actually, you think about everything in 2D, these are the directions that it's really allowed. And for an x1, x2, this is the gradient update to be positive, or all the gradient to be negative right here. So they can only be all positive or to be negative, right? So this is something that you can only do here. But if the ground truth, the optimal W vector should go this way, which is shown in the like blue vector. So what you are doing with the sigmoid is you are only doing the zigzag path because you can only take this direction, which is light into the third quadrant. Then you can only take the and a gradient in the first quadrant, then third quadrant, first quadrant, third quadrant, first quadrant, and so on. So you are actually taking a zigzag path to do the optimizations because
Are you saying that the convergence will never happen, take too long to happen?
it will converge, but you are like wasting a lot of resources because you like implicitly assume all the component has to be all positive or negative.
Gotcha.
Yeah, so it's like alternative and the least square, but this time we know exactly the gradient, but we are just use the a sigmoid and implicitly restrict our gradient update direction to be in the first quadrant and the third quadrant. Okay, so this is only for the stochastic gradient descent if you have only one single element. If we have one single element, this upstream gradient will be exactly to be the scalar. Then you will always have that kind of all positive and all negative and the problems. But of course, if you have a mini batches, you can have a positive and a minus, and a positive and the negative part. But still, this statement of this one is still true, right? So this and the sign of gradient will have the exact same sign of upstream and upstream like gradient. So this is something that you have to keep in mind. If you want your model to be powerful, that means you want your model to, when you train your models, you should have a lot of and possibilities. If you restrict your models into certain patterns like what we are having here, actually it will hurt your training, and it will hurt your models as well. Okay, so this is the second problem. The third problem is exponential function. It's quite a bit, computational expensive. This is not really an issue in general, but actually, if you really compute the exponential a lot, it will become an issue. In terms of speed, because in uh, Python, what they really do, trying to calculate the exponential function, is they use tail expansions, right? So this is getting like less efficient compared to the polynomials. Okay, um, so another way, like for the second one, that the sigmoid output is not zero center, it's very easy. All we need to do is we just use the hyperbolic tangent. Then it will squash the numbers to the range of -1 to 1. So the output will be like around 0. Okay, so this is being actually uh, proposed in 1991 by Yang LeCun. So it's almost like 34, like nearly 40 years, like 35 years ago. So, but still have a problem because it has the same issue of the gradient vanishing. It can still kill the gradient when being saturated. So, funny things is it's always people will propose many different activation functions. Gradually, they find this is working very well. Then the mathematician or applied mathematician will come in trying to give some explanation why this activation function is doing a good job. So this is a funny field that I'm actually, so the engineering goes to first, then the mathematician comes to next, right? So this is like, and usually kind of flipped. Okay, ReLU is another one that is very popular. So, it's very simple, maximum of 0 and x. So ReLU is short for like an rectified linear unit. It doesn't saturate, in positive region, obviously, because you can see this goes straight up. And very computational efficient. It's only linear in the positive domain and 0 in the negative domain. It actually converges much faster than sigmoid and hyperbolic tangent. And for example, it's 6 times faster converges. So there are two issues. One is this is not zero-centered output, right? So you can see every output is between 0 and the non-negatives. And also there's a bit like annoyances like here. One thing that you can think about, what is the gradient when x is less than 0, which is always 0. So let's review this question again. If we have the problem that x is equal to -10, and of course the gradient just goes to 0, right? Because just like that would be literally straight 0. If x equal to 0, then that's really undefined, right? So this is the point that you hope you don't hit a 0. If it is x equal to 10, then like partial sigma partial x just give you 1, right? So this is like a like linear line. So if your solution actually hits into these directions, that your output is always give you negative values, right? So that means you are just like turn everything into 0, right? That is kind of well happen. That's possible, right? So if you didn't choose or initialize your weight correctly or make whole things correctly, that's very likely to make your whole weight to be like all negative. Then after passing the ReLU, everything just becomes zero. Then you will never activate, will never update, right? So this is basically if you didn't choose your initial weight correctly, if you apply ReLU, your neural network is dead. Like it cannot be recovered. And something that is will not happen in sigmoid because no matter how saturated the neuron is not dead. But in ReLU, it could be dead, right? Because everything just goes to zero, kills everything, which is really bad. So this is something that is the active. So that means under some region, it might be have some positive values. Under some regions, it might have a negative value. At least some data point you can get a positive like component. But this is really bad, right? So everything just gone. So that means I mean, if we really want to and work on ReLU, we want to initialize the neuron with the slightly positive biases. So that means it can hope at least to get some like neuron to be activated, right? So you don't want to have a dead neurons. Okay, so to really solve this problem of the dead neuron, there are, as I think like 12 years ago, people start to think about what is the best strategy to solve this dead neuron problem. So that's why this is called leaky and leaky ReLU. So this is very similar to ReLU in the region of -10 to 10, but the difference is like when it's like less than zero, the function will behave like 0.01 times x instead of zero. In this cases, then the neuron will not die. If it is less than zero, it just behaves like very, very slowly, right? And of course, you can, I mean, 0.01 is very ad hoc values. You can actually do and treat this as a parameter. So you can treat alpha being a parameter and like the weight. So you can treat this and alpha to be the parameter. You can backward propagate this alpha if needed, such that at the different layers, you will have a different and like leaky ReLU and the parameters if you need it. So this is like, yeah, go ahead.
Oh, the alpha changes at each neuron.
Yes.
Oh,
Yeah.
okay.
So this becomes like an a parametric and the rectifier. So, right, and it's everything can be backward propagated, right? So this is the way that okay. I mean, if you don't like 0.01, I'm going to set as a parameter. You can do backward propagations to find optimal alpha if you need it. Right. So this is something to make it slightly more generalized than leaky ReLU. So this is really it's unbelievable just 10, 12 years ago, right? So like people are still working on that very fundamental problems in the activation functions. All right. Okay, so then this is and this is also extremely and popular. It's called like ELU, so exponential linear unit. So you can see almost everything compared to uh, like leaky ReLU, everything if it is x bigger than zero, it's always equal to x. I mean the difference is if x is less than zero, so and how you change everything, right? So I mean everything will become slightly negative, but it's like being shifted down a little bit, right? So this is something that you will see here. So in this case, it's by default is 1, so that would just be like an exponential x minus 1. As x goes to minus infinity, this will be goes to minus 1. So this is the minimum that we get is minus 1 in this case. Is the maximum is just goes to infinity. So so in this cases, it will be closer to the zero mean output. You have some negative values. you have some positive values, right? But like most of them are positive. Um, so the negative saturated regions are comparable with the leaky ReLUs. So you can think about it with the small regions, this look like a leaky ReLUs. But it will add some like robustness to the noise. One of is why we say that is in this case is as x goes to like negative infinity, this whole thing can actually goes to infinity, right? So the domain of this function is actually from minus infinity to infinity. But in this cases, the domain of functions actually is from -1 to positive infinity. So in this region, it will not goes to like minus infinity. So it will just ensure this at least is lower bounded. Um, and of course, we still need to require to calculate this exponential functions. So this is actually 2015, right? So this is like literally 10 years ago for these ELU functions. Um, there are more, right? So this is called scaled exponential linear units. This is 2017, right? So this is a scaled version of ELU that turns out shown it's work better for deep neural network. Um, so like this is has other like um, like beautiful like properties. I'm going to talk about this a little bit later with the like batch norm, but it can train this kind of CLU networks and very well. Um, but if we, I mean, so if we so actually plot this out, it looks very similar to ELU, right? But it's getting a little bit slightly more negative than ELUs. So the difference is very minor. It just performance is getting better, right? So if we're using this kind of scale versions. So the difference is it just we simply add a one lambda here, right? There's no other thing fancier than that, right? So it's kind of weird because a very simple twitch in neural network can actually have a dramatic like effect to the whole performances. So just adding the lambda in the front and actually can make whole thing a lot better. So that's why it's actually worth a paper, right? Just adding a lambda, you just redo everything. Okay, so and also this is and a max out. This is not really being used a lot, right? So I just and let you know there is something called max out. Basically, you have a two different linear transformations, then you just pick the maximum out of that. It actually generalized the ReLU and the leaky ReLUs, but of course, and it doesn't saturate, it doesn't die. It's all linear regions, but we have a double numbers of parameters. I actually haven't never seen such kind of like activation function in practice being used. Um, but just let you know, so it could happen. Um, these are so a little bit more than one. So this is called swish. Um, so swish is something like that. So you still have a sigmoid here, um, and you have a parameter of w. Sorry, and a beta here. So it's basically x times sigmoid of beta x. Right. So this is so like the function you will see is looks like this. If you choose beta equal to 1, it will be really look like ReLU functions, right? So you have something get slightly smaller than 0, then going up. Okay. So this turns out this switch activation output and outperformed all other options. That's 2019, right? So designing a good activation function is definitely worth a good papers. So like at that time, Cypher 10, which so is the data set that you're going to use, is one of the benchmark data set. So so they train a neural network to generate and test out with different like nonlinearities. They find out this switch activation functions is doing a very good job. So this is so one of the choice. I'm actually so right now people use CLU, Swish. They are very like both are very popular as activation function. There's another one called GLU. GLU is also another one that is so very popular. So that one is 2016. It's almost 10 years ago. So so you can see this GLU and the Swish, they look very similar. Right. So this is getting a little bit negative values on the like negative domains, but uh, but it's not super negative. But when it's like positive, it's always goes straight up. Okay, so that means for the largest and the larger value is more like multiplied by 1. For small and a small value more like multiplied by 0, like ReLU, right? But we are basically take expectation of the randomness, and what does that actually means? Is basically if we take x is a random number with a 0 mean and a standard deviation equal to 1, what we do is we take expectations. No, sorry, I mean, so x times the probability of the random variable less like equal than x. So this will be my GLU. So the differences between Swish and the GLU is you can think about I'm actually choose the beta equal to 1.702, right? So differences. That's the differences. Like Tensor can do like pretty good job. So you can see this is very interesting. So in the early stage of neural network, if you can design a good activation function, even though you just pick a numbers, 1.702, you can perform really well. You can like publish a paper, right? So this is very common choices of GLU in transformers. We're going to talk about transformers in 593. Okay. Okay. So there are a lot of take-home message, and unfortunately, we use sigmoid as a function. As one example. But here, take-home message is don't use sigmoid, right? It's bad. So use ReLU, use GLU. In transformers, try leaky ReLU, ELU, CLU to squeeze out some like marginal gain. If your performance is getting 85%, if you want to get 87% or 86%, you can twitch with that kind of and activation functions to squeeze out some marginal gain. But if you want to get 90%, 95%, this won't be helpful. So you want to understand something. Fundamentally, if you want to have a big leap in your, in terms of performances, finding the best activation function will not be the choices, right? So this can only give you marginal gain, right? 1%, 2%. But fundamentally, if you want to get big gain, you actually have to pick the right models to work with. Okay, if you're using ReLU, you have to be careful with your learning rate. All right, so that's the activation function. So you can see there are a lot of activation functions. A lot of problem is very engineering, so it's very ad hoc. In the homework, you actually need to go through these activation functions. You actually need to implement all these activation functions from scratch. Data pre-processing is a very important one. So, for example, this is the original data right here. It has the ellipsoid. It's not centered at 0. So the first thing that you can do is you can actually subtract the mean to make sure your data is shifted into the origin. Then you can actually normalize with the standard deviations in each axis, right? So this is I mean, this is called whiteout. So we will talk about data pre-processing in 593 as well. I mean, this is a very important process in like machine learning. So because before you actually apply any kind of like machine learning, deep learning process and models, this data pre-processing is one of the most important part. So um, so that's why I mean consider like the one that we have, right? So we have the neuron always like say the output is always positive. As a result, actually my allowed gradient update is always zigzag because the allowed gradient update can only be in the first or third quadrant. So they can only be that, I mean, gradient can only be all positive or negative if we use the stochastic gradient descent. Okay, so that's also why you want the zero mean data, right? You want some data to be positive, some data to be negative, such that you don't have the restrictions for that kind of update. If you have that kind of update, your training will not be efficient. Okay, so data pre-processing. So this is kind of I mean normalization. We have talked about this kind of data normalization before. And you can refer to the Lasso and that notebook. We have talked about data pre-processing. So this is called like normalization. Everything being shifted into zero mean and the standard deviation to be one. So, so after normalization, it will be less sensitive to small changes in weight. It's easier to optimize. If we like before the normalization, it might be very sensitive in the weight matrix. It will hard to optimize. So that I mean, happens a lot if you have the uh, like the data matrix has a different scales. Some values is like super big, some values super small. Okay, so I mean, this is something and also you can also see the PCA as well to be one possible like pre-processing methods. We have a talk about PCA, I mean, as a pre-processing method in the PCA notebook. I mean, so you go to the PCA for the data, then you just apply the SVM hinge loss, like soft and the soft and the softer margin ones. So this is also the one. So you like PCA is a common data pre-processing strategies. Okay, so I don't want to get into too much details. There are a lot of practice for images. Usually for images, the best choices that you do is you subtract the mean images, right? So like just do the center only, um, because you don't want to change the variances because change the variance sometimes may change the quality. But center the image will definitely help. So for the Sci-Fi 10, examples, you actually have a 32 by 32 by 3 images. So everything is color. So 32 by 32 is pixel values. And 3 is actually the RGB values. So this is actually a tensor. So each like RGB images, it's actually a three-dimensional tensors. So what you actually do, for example, what you can do is you can subtract the main image, which is like as being used in the AlexNet. So all these things we're going to revisit that in the 593 because in 593 you're going to work with these kind of like real large data sets, like AlexNet and something like that. Yeah, and you can also like subtract per channel means like channels is RGB, right? So like red, green, like blue. So each channel has its own means, right? So and you can subtract the means along each channels. So that's being used in VGG. Um, And also you can do the subtracted per channel mean and divided by the channel per channel standard deviation. That has been used in like ResNet. In image processing, it's not common to do PCA and widening before you use this kind of like deep neural network, right? So for deep neural network, so you can subtract the mean, you can divide it by standard deviations, but you still want to keep the variances as it is, and each component variances as it is. So it's not common to do the PCA and windings directly here. And although for the machine learning, it will be quite common to do the PCA and the windings first. So this is the differences. Okay, so this is a very quick thing about the data pre-processing. For the whole data pre-processing thing, we're going to cover that in 593. So this will be a whole lecture in 593. Weight initialization. So this is a very important. It turns out how you initialize this weight of the matrix is extremely important. Say if you use a constant matrix, W, for example, all the weight are the same, right? And what will happen? Actually, let's try something like that. First is a small random numbers, Gaussian with a zero mean, and standard deviation is 0.01, right? Each weight, it's like you have a D in and a D out. D is dimension in and a dimension out. But this one works okay for small neural network, but the problems, well, with the deeper neural network. Why? So let's look this extremely carefully. So we have 6 layers of neural network. Each hidden size is 4096, right? So this is a lot. And for each one, I'm just like generate some random data of X right now. So what we do is I'm just doing forward propagations, right? So this is my W. I initialize my W, and I just simply do linear transformation, and I apply the hyperbolic tangent. And then I keep doing this, right? So this is nothing but doing the forward propagations. But what will happen to the activations for the last layer? So what you can do is we start with some like random like Gaussian, so X. Just a second. Why? 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 Yeah, just the email. Okay, that's fine. So okay, so uh, the behavior looks very weird. So if you look the first layer, actually the standard deviation is 0.5. Uh, but as the layer getting like passing through the the value, all the activations and after activations will concentrate around 0.
Why is that bad?
It's bad because the output will all have similar values. That means it has less power to make any kind of good predictions. A good model is being considered as has good express abilities should have a lot of varieties.
Yeah.
So the variation should be large.
And so this is what the activation function is getting.
So after activation functions, everything being concentrated around 0.
I see. Okay.
So that actually is not a problem of the activation function from the and hyperbolic tangent. It's actually coming from the reason is coming from the W's, the initialization of the W's. Yeah, and I want to remind you my W is 0.01 times the like Gaussian random number of D in and D out. Okay, so let's just look at this the gradient and the gradient here. So they are all zeros and with the very small variations. So that means if it is all zero, then so essentially they won't have any like learning going on here. So why this happened? So what I'm going to do is I'm change the initial weight from 0.01 to 0.05, right? So like increase a little bit. Actually, this look like that. The gradient is no longer has small variances. It actually has like, and you can see this like, and the output of the layers will be no longer concentrated at the 0. It actually concentrated either -1 to 1, and it has a very strong like transition between like both. So the variance is like pretty large in these cases, which is about 0.85. The only difference is I changed from 0.01 to 0.05. You can test it out. I mean, this is the code that you can just plug in to see the statistics. So this is, and this is also really bad. Why? Because all my values is being concentrated as -1 to 1. That means all my neurons actually are saturated. That means the like local gradient will all be 0 again. So there won't be any learning at all. So here, what we have is the value are tending to like goes to 0. So there's no variances. When we increase the W, actually all the neurons will be saturated. There will also be no learning at all. Okay, so then what can we do here, right? So this is this is very delicate, right? So we just changed from 0.01 to 0.05. Suddenly, then all the neurons like saturated. Actually, what we can do is we can just divide it by the square root and the square root of d dimensions, right? This value is actually between 0.01 to 0.05. So that means there will be a sweet spot between 0.01 to 0.05 to make sure the output is somewhere in between, right? So this is bad. This is bad. If we choose this square root of d dimensions, it looks like this. This will have just a right amount of the output. It will not concentrate at 0. It will not being fully fully saturated at -1 to 1. So all the activations are nicely scaled for all layers, right? So you have a good amount of variations, and the values is like so nicely distributed between 0 like -1 to 1s. All right. So this is for convolution layers. That's different story. But here you see, this is called Xavier initializations. So that means if you just don't times the right coefficients, your training will just go disasters. Right? So this is very important. You see, this is very delicate in the weight initializations. If you don't choose the right amount of the initialization weight, your result will go bad. Right? So there are some theoretical reasoning why this is correct, and actually deeply related to high dimensional probabilities. Right. So there are a lot of weird probabilities, like results when your dimension is getting really high. Okay, so why it is like that? I have a very naive explanation here based on this Bengio's 2010 papers. So we know we are taking some linear transformations, right? X dot W. We assume X, they have the same variances, right? So this is what we have here, right? So we assume our X's have, it's a Gaussian noise with a mean 0 and the variance to be 1. So that means each component have the same variances of equal to 1, okay? So the whole idea is I want my Y should have the same variances of my X, right? So what we do is we plug in this, substitute y by this linear transformation. So because each of that are sampled in the IID manner, right? So everything is IID. So I can pull out the D in, which is the dimension of input out. And then that becomes the D in times the variances of Xi, Wi. Here we assume all Xi and Wi are IID sampled. And we assume they have a zero mean, and obviously they are independent. So I can separate the variances of product by product of each variances. So that means if we want the variance y equal to variance of xi, the only way that we do it is we choose the variance of wi is 1 over d in. Right? It's that simple. So that's the reasoning why you actually have to choose your w is being the standard deviation of the w is 1 over square root of d. That's it. Okay. 15 years ago, if you can find this, you can write a paper. All right. So because this explanation is clear, working, useful, as a name and attached to this, Xavier initializations. Okay. But if we change everything, and I want to remind you right here, we are using hyperbolic tangent here, right? If we actually change to ReLU, we use the same Xavier, it actually is wrong. Again, so everything will concentrate at 0. There will be no learning.
Oh, so I actually completely missed that. We were doing it on
Hyperbolic tangent.
both.
Right here, see? Afterward. Yeah, so hyperbolic tangent has a 0 mean, right?
So initialization really depends on the activation.
Yeah, yes. That's exactly the point. So if we choose the ReLU, there will be a huge amount of the value will be concentrated at a 0 at layer 6. All the activation collapse to 0. This is bad. One of the reasons is if we're using Xavier initialization, it assumes the zero-centered activation functions, right? Because what we have is we have this assumption that everything has a Gaussians. Start with the Gaussians, and after we output, it will still be a Gaussian because Gaussians and the multiply Gaussian and the linear combination of Gaussians is still Gaussians. But this is not true for the ReLU because ReLU make everything to be non-active. So that's why just the right choice of initialization, there will be a correction for ReLU, which is standard like square root of 2 over the dimensions. This is just the right activation. Just will be nicely scaled for all layer. You can see all these things. It's just you have a right amount of zeros. You have a right amount of the positive part. So this is called Kai-Ming, like and it's initialization from Kai-Ming He. That actually is being proposed exactly 10 years ago. Okay, you do those kind of similar analysis, but you have to assume everything being non-negative. Right? So that's why instead of you have square root of 1 over d in, you have square root of 2 over d in. That actually will do a much better job for ReLU activation functions. So that means each activation functions, it will have its own correction terms, right? So this is the like reasoning right here. So you want everything after the like and passing through the data, you want your output is roughly evenly concentrated. You have enough value being either concentrated 0 or positive part, and you don't want your neuron to be saturated. Okay. So this is proper initialization is a very active research until pretty recent. This is a very good like area to work with 7 or 8 years ago, but probably not anymore. So the machine like deep learning is a field that evolved extremely fast, right? So when I look these things, I'm like looking like dinosaur age, right? So each year the whole techniques evolve like speed of light. Uh, they have a complete different philosophy, like different approach anymore. What is being used here is really like dinosaur age in the scale of deep learnings. All right, so at last, I want to talk about batch normalization here. Okay, so unfortunately, batch normalization, I'm not going to test that in the homework, but this is obviously a very, very important concept. Um, so the whole idea is you want everything output of the activation, so after output like its activation, has a 0 mean and the variance of 1. Right? So this is a very common assumption because you want everything just to be nicely Gaussian distributed. So, and obviously after that, activation functions, usually they don't have that kind of behavior. So the batch normalization says, I will make them to be 0 mean and unit variances. So what you do is you're going to consider a batch of activations at some layers. So this is actually you get a batch of the activations. Then what you do is you make each dimension has a 0 mean and a unit variances. Very simple. Subtract mean and divided by the standard deviation for specific layers of the output, right? So you get the statistics. You know the output of the layer will have that kind of mean, that kind of standard deviations. You just apply this linear transformations. This is really good because this is a vanilla differentiable functions, right? So this everything is a linear. So that means what we did is we actually, after activations, we apply additional linear transformations, right? So this is additional linear transformations for pre-calculated mean and pre-calculated standard deviations. Okay? So what you do is you have this input that you have n by d. For each channel, you calculate per channel mean, you calculate per channel variances, then you normalize it, right? Um, so and also, I mean, this is like very straightforward. Like, I mean, it's like white out. But if we have a zero mean, univariance is too hard of the constraint, and sometimes that's not possible. Like for example, the output of ReLU, right? I mean, it's always non-negative. So you can also make this whole thing to be a scalable shift parameters, right? So by the end of the day, what we are trying to do is we want to apply some like uh, uh, and like so nonlinear sorry, a linear transformations to do the normalizations, right? So what we do is we actually are taking this gamma and the betas, right, to get this wise. So that means after activation functions, we are applying a simple like linear transformations. Actually, hopefully we can scale it well. So this is, and of course, if we choose the mu and the sigma, that's exactly the one that we are looking for to widen it out. But as I said, you don't need to. You can learn this parameter as well, right? To have a better skills if you need it. It's always the the whole philosophy is if you feel this approach will work, make this a parameter. Use backward propagation to learn it, and hopefully, the data will tells you what is the best scale methods here. Okay. Um, so this is very important. So this actually per channel mean per channel variance is estimated depends on the mini batches. So you cannot do that. I'm at the like test time. So that means these mean and the variances are all pre-computed from the trainings. So you cannot modify that part. Um, but during the training, we are doing the running averages of the values seen during training, and also same for the variances as well. So, however, during testings, this just purely becomes a linear. The mu and the sigma being fixed. Um, so this is like a slightly different idea. So this whole thing, batch normalization is kind of different if you work with the training and testing, because training, you actually have to estimate this mu and the sigmas, like and as the data feeds in and getting bigger and bigger. But in the testing, that you can lock down what is mu, lock down what is sigma, then you can treat everything to be purely a linear operator here. Okay, so that is something like you would do, right? So previously you have, FC is called fully connected, like layers, like and what we had before. Then you apply the sigmoid, which is hyperbolic tangent. In between, you're going to insert this like batch normalization before this activation function. So this is just a simple like batch normalizations that we have, right? So you estimate the mean, you estimate the standard deviations from these mini batches, such that to make sure the data is the output of the activations is roughly like with the zero mean and like standard deviation to be one. So like such that everything should have the like the right scales, right? So this is very important. Okay, so this actually will make whole deep neural network much easier to train, because one problem to make this and the like training is so difficult is at each channel, or like at each like and a component, the value scales too much, right? For example, x1 scales from minus 10 to the 6 to 10 to the 6. The x2 only scales from minus 1 to 1. Then this whole thing makes impossible to tune at all, right? So this is really, really bad. The deep neural network will and works very well if both of the channel or like component scales between minus 10 to 10, right? So this will works very well. So that's why This batch normalization actually makes the whole deep neural network much easier to train. It can improve the gradient, so you can calculate the gradient nicely, and it can allow higher learning rate and fast convergences. Think about the one that you had for the minus 10 to the 6 to 10 to the 6. If the value is that big, the gradient will also be big. So that means if the gradient big, then your learning rate has to be super, super small, right? If your learning rate is super, super small, then your converge time will take longer, right? So this is the whole logic here. The network will be more robust to the initialization. It can think about as a regularization during the training. Um, and also in the testing time, there's no zero, like there's no overhead at all. I mean, in this case, I don't want to talk about convolution layer. This will be taught in 593. But the issue is the behavior will be different during training and testing because training and testing doesn't necessarily to give you the same mean and the standard deviations. You have your trained mean and trained the standard deviations, but your testing may look different. So this is a common source of bugs uh, from the batch normalization here. This is convolution network. I don't want to get into too much here. There are other ways that you can do. It's called, I mean, this is this is basically the batch normalization. So basically, you have a data of n by d. You normalize it, find out the mu and the sigma, which is 1 by d, right? Or you have some gamma and a beta, which is you can train it here. Then you apply this normalizations here. But there's another one that is you can do is called layer normalization. So there are two different normalization strategies. In the batch normalization, we normalize with the data. In layer normalizations, we normalize the dimension, which is channel. Now it will have the same behavior of training and testing no matter how we do this because we are getting n by 1 here, right? So then what we are getting here is we are like and literally and just normalize with respect to the channels. So this is like slightly different um, uh, choices of normalizations. Usually, batch normalization works on computer vision problems, images, and as images like videos. Layer normalization usually works in large language models, like language models, um, as NLP problems, sequence problems, right? So this is something being used a lot. So this is being proposed by Jeffrey Hinton's group. Uh, Again, 10 years ago. Um, there are other things for convolutions like that. I'm not going to talk about this, but I just want to emphasize there are many other like normalization strategies for that. Group normalization, no, that's not really important. Okay, so here is what we did there. So take home message, it's almost there. We talk about different like activation functions. Right now, people use Swish, ReLU, GLU. So this is commonly used activation functions. Data pre-processing for images, subtract mean will be enough. Weight initialization depends on the activation functions, right? If it is hyperbolic tangent, use Xavier. If it is ReLU, you're using Chi-mean initializations. You need to use batch normalization if you are working with a computer vision problem. If you are using and work on NLP problems, you need to work on layer normalizations. All right, so that's everything I want to talk today. It's very brief, uh, but hopefully a lot of informations. Okay, I'm sorry.